Okay, this is Jack Jackson back again, and we're looking at some more examples of triangular distributions. In this example, we're going to look at one that's in 4 pieces. So 2 of them are actually 0. So let's look at this. In general, what's the coordinate of the maximum point in general? We've actually worked this out before. We know it's m for the x, and then the y is just the height of the curve, height of the triangle, the overall height. Well, the base is b minus a here, and the height turns out to be, well, whatever the height is, let's just call it height for right now. The area, which is 1, is 1/2 times b minus a. b minus a times 1/2 is b minus a over 2. Multiplied by its reciprocal times 1 is just 2 over b minus a, and that equals the height. So the height is 2 over b minus a. So the coordinates of that point at the top are m, comma, 2 minus b over a. And that's true no matter whether m is all the way at the left end, the right end, or in the middle. In this video, we're going to look at an example where it's in the middle. So our PDF is going to have actually 4 pieces. 2 of them are 0. Those are easy. But it's going to have, even in the important part, it's going to be a piecewise defined function with 2 important pieces. So we're going to have a formula for each of these separately, in other words, to be able to figure out heights here. And this one on the left, going from a0 up to m, comma, 2 over b minus a, that's going to have a positive slope. And then going from this top point down to b0, that's going to have a negative slope. So let's write down the formula for it and draw out the graph. Well, I've already drawn out the graph. First of all, as we've seen, the height there is 2 over b minus a. So b minus a is 6 minus 2, that's 4. So in other words, it's 2 over the base. So 2 over 4 is 1/2, and that's the height. Let's just check it out again. Make sure the area is 1 is required. It's 1/2 base times height. So it's 1/2 from 2 to 6, a base of 4. So it's 1/2 times 4 times another half. That is 1, and that's what it's supposed to be. So that's good. The easy part's the outer 2 pieces, which are just y equals 0. Now the inner 2 pieces, we need to figure them out. So we need to, but we have, either case, we have 2 points. We have the point 5, 1/2, and 2, 0 for this point. So we can do a slope x-intercept form of that graph, that line. And for this one, which will turn out to have a positive slope. And on this one over here, we have a negative slope, and it's going to have the point 5, 1/2 and the point 6, 0. And we can figure out the slope there. So let's see if you can go ahead and figure out the left one first, the one with the positive slope. When you're done, come back. Well, did you come up with 1/6 times x minus 2? X minus 2 being in parentheses. Well, we know it goes through 2, 0 on the x-intercept, so if we put the x minus 2 in parentheses and just put the slope out front, this will go through 2, 0 because 2 minus 2 is 0 times whatever the slope is, that's 0. Now we just need to find out the slope. Well, the slope is delta y over delta x, or vertical change over horizontal change. As you go from this point here to this point here, we go to the right 3, 5 minus 2, that's 3, so delta x is 3, and we go up 1/2, so that's 1/2 divided by 3, which is 1/6. Or do y2 minus y1 over x2 minus x1, 1/2 minus 0 over 5 minus, let's see, 2. Okay, so that's 1/2 over 3 either way, which is 1/6. The x-intercept is 6, 0, so the PDF of x is 1/6 times x minus 2. That's for this increasing part. Do the same thing for this one here. Don't forget you're going to end up with a negative slope. Press pause. All right, you should have gotten the slope of negative 1/2, and it goes through the x-intercept of 6, 0. So we know that this is x minus 6 in parentheses times the slope, and the slope was negative 1/2. In this case, we're going to the right one, and we're going down 1/2. So the slope is negative 1/2. Okay, and then we get x minus the 6. So if you write out the entire formula, and I graphed it in blue here, here it is. It's 0 for x is less than 2, 0 for x is greater than 6. Those are the 2 outer pieces. The middle pieces, the one they're important, that is going up, 1/6 times x minus 2, and then this part that's coming down, negative 1/2 times x minus 6. Now, why do we need this? Well, we need this if we're going to find different heights. So what's the probability that x is less than 4? See if you can shade it and work this out. Press pause now. Well, hopefully you came up with a triangle here to the left of 4. So we're just finding the area of that triangle. It's 1/2 base times height. The base is 4 minus 2, which is 2. The height is, well, how do I find the height? That's why I need this formula. I just plug in 4 in the formula. Well, which part? Well, 4 is between 2 and 5, so we're going to do this part right here with the positive slope. So 4 minus 2 is 2. 2 times 1/6 reduces to 1/3. So the height right here is 1/3. That should agree with the grid. Looks 1/3 is 0.3 repeating, so that looks pretty close there. That looks good. So the area is 1/2 times base times height. That's 1/2 times 2 times 1/3. That's just 1/3. All right, time for you to try another one. What's the probability that x is greater than 5? Well, hopefully you came up with this triangle. And again, we could, now this is the height here. We know, we actually figured out that height earlier on as being 1/2. Okay, or you could plug the 5 in either formula and get it, because that point right there is common to both of these lines. If we plug it in this formula here, 5 minus 2 is 3 times 1/6 is 1/2, so that works out. If we plug it in here, we get 5 minus 6 is -1 times -1/2 is also 1/2. So either one of these formulas will give us the same thing where they touch each other, and that's the thing we worked out at the beginning anyway to figure out the formula, so we knew it was already going to be 1/2 for the height. And the base is 1, so it's 1/2 times 1 times 1/2 is 1/4. And that's a typo. Let's fix that. And of course 1/4 is 0.25 or 25%. All right, here's another one. Same graph, same formula. Find the probability that x is between 3.5 and 5.5. Press pause and work this out now. Okay, so we're finding the probability that x is between 3.5 and 5.5. Hopefully you figured this out already, and you're back now to check your answer. So when you did this, did you come up with a shape that looks like this? This is actually it's a pentagon, I guess. It's got 5 sides to it. But we're going to think of it more in terms of the unshaded region. So the unshaded region is just 2 right triangles. So the probability that we're looking for is the shaded area, which is 1 minus the area of those 2 triangles. So it's just 1 minus triangle 1 area minus triangle 2 area. So the first one goes from 2 to 3.5. And the second one goes from 5.5 up to 6. All right, so on this one, from 2 to 3.5, that's 3.5, or 3.5 minus 2 is 1.5 for the base. The height is, plug in the 3.5 in the formula. All right, there's the formula. Okay, and which part are we going to use? Well, this is on the part where there's positive slope, so that's the part we're going to use. X is between 2 and 5, so we use this part of the formula. So, but we plug in 3.5. Let's see. 3.5 minus 2 is 1.5, divided by 6 is 1.5 divided by 6 is 0.25. We can just kind of check that real fast. So it's 3.5 minus 2, and then divide by 6. 0.25, or of course you could change that to fraction. You know how to do that. That's 1/4. So we have 1/2 times 1.5 times 2.5. So 1/2 times 1.5 times 0.25, and that gives us 0.1875. Now what is that? That's the area of this unshaded triangle right here. All right, how about the other unshaded triangle over on the other side? Well, it just has a, so you got 6 minus 5.5, that's 0.5 for the base. And the height, you plug in 5.5 in the formula. But 5.5 is between 5 and 6, so we use this formula. That formula says it's negative 1/2 times 5.5 minus 6. That's positive 0.25. So that's the height here. Notice that the height, whether it has positive or negative slope, the heights should turn out to be positive numbers. All right, so now let's work this out. Negative 1, well, not the negative, let's just say 1/2 times a base of 0.5 times a height of 0.25 turns out to be 0.0625. If you like fractions better, that's 1/16. And we plug it in there. So that's the height, that's the area of this unshaded one here. Well, the shaded area is 1 minus these two unshaded areas. So it is 1 minus 0.1875 minus 0.0625, which is 0.75 or 3/4. Now, a couple more little things. It turns out, of course, the mode is given to be m, and without proving it here to you, it turns out that there's a really nice formula for the mean. It's a little bit, maybe not obvious at all that this is true, but it does have a nice formula when the dust settles. It's a plus b plus m divided by 3. So you just average the three numbers that you're given up here, and that gives you the mean of the entire distribution. The proof's going to require a little calculus, so I'm not going to go over that now. I might add some slides at the end of the whole slideshow, which would be optional slides that could be omitted, whether you know calculus or not. But it will show some of these derivations, such as maybe this formula, particularly for the folks who have studied some calculus. Might want to look at some of those slides, but again, those slides, if I make videos out of them, those videos would be completely optional for my class. You can completely omit them whether you know calculus or not. But let's look at a couple of examples now of the PDF and CDF together. The CDF's in red. The PDF and the CDF are on top of each other right here, so the blue's on top of the red. From negative infinity up to whatever a is. And in this case, a is 2, b is 12, and I have the CDF in red and the PDF here. Actually, turns out when this is a straight line, this is part of a parabola. Okay, and so we have a horizontal piece here, concave up here. When this reaches a max, it switches to concave down here, and then it hits a horizontal line here and stays there. So this is not an actual asymptote. This actually is y equals 1 to the right and y equals 0 to the left. Okay, but anyway, this one I have the median exactly halfway between the a and the b. And when you have this, you can tell that it's completely symmetric about this. So the mean, median, and the mode are the same. In this case, it's 7. So if you average 2, 7, and 7, so this is 2, 12, and 7, excuse me, you get 2 plus 12 plus 7 is 21 divided by 3 is 7, and that's the mean. The median, it is also 7 because you can see half of the probabilities to the left, and I have that half shaded, and I have the y value of a half on the CDF curve. You can see that. And the mode is also the same place because it is definitely the last number, and that's the highest point on there. So the mean, median, and the mode are the same on this one, and we get perfectly symmetric graph, zero skewness. Mirror image, vertical line symmetry shows that this shaded triangle is exactly like this unshaded one here. This half is a mirror image of that half. You get rotational symmetry on the CDF. If I take this point that I've got marked with X right here, which is 7, 1/2, then you can spin the graph 180 degrees, and this part to the right will be on top of what's now to the left, and vice versa. So it has rotational symmetry. or point symmetry. Now, what if the mode, this is with the mode exactly halfway between the A and the B. What if it's actually a little further to the right, let's say? So let's put the mode over here, say at 10. I'm still going from 2 to 12, but I'm putting the mode closer to this end. So the mode is over here. Well, it turns out, let's just use our formula for the mean, A plus B plus mode divided by 3. So 2 plus 12 plus 10, that's 24. Divided by 3 is 8. So the mean is right here at 8. And by sliding this thing across, I found that the median was, looks like about 8.3 or 8.31, something like that. And that gives us a y value of 0.5 on the CDF curve, or an area of 0.5 here. But notice it's a little to the right of the mean, and the mode's even further to the right. So they're in kind of an increasing order. Mean on the left, then the median, then the mode. And this is skewed to the left. Remember our skewness on the PDF graph. If our tail is longer to the left, that's going to be skewed left or negative skewness. So of course, it's exactly backwards if the mode is a little bit closer to the left end. So this time I'll put the mode at 5, which is a little closer to 2 than it is to 12. And so this one's going to be skewed to the right. More of the probability is kind of concentrated on the left, more spread out on the right. That's called skewed right, or positively skewed. In this case, the mode, of course, is given to be 5. The mean, if I do my formula, 12 plus 2 plus 5, that's 19. Divide by 3 is 6.3 repeating. Okay. And the median, well, I did it by just sliding across to find it here. But according to what I have here, the median looks to be about 6.09. And then we get a probability to the left of that of 0.5. So it looks like we have mode on the left. That's the highest point. The median, where the area to the left or probability to the left is, the probability to the left is 0.5. That means the area to the left under the PDF is 0.5. And it also means the y value on the CDF, which is the same as this vertical distance right here, that this point is above the x-axis, all of those are 0.5. So that's the median, and the mean's a little bit bigger than that. So they're in the order mode, median, mean in increasing order, and that's when we're skewed to the right. So in general, skewed right is going to pull the mean above the median. In this case, it's above the mode as well. So hopefully these little videos have given you some idea about triangular distributions. And again, you know, it's not such a big deal about triangular distributions. The main deal here is that we get some practice visualizing these things as areas, and we get to understand that the PDF graph, under that, the area is the probability. A little bit different than the CDF, where it's the y values or vertical distances or probabilities.